Good morning. It's raining and I'm having coffee. Want a cup? Come by my office. Okay, we're starting chapter 5. Chapter 5 deals with normal distributions, whatever normal distributions are. And I want to remind you that when we were talking about probability distributions in chapter 4, we had two types. We had discrete and we also had continuous. So this is probably our most popular continuous probability distribution that we see in 5.1. Okay, so let's have a small conversation about normal distribution. And I know they do a good job of this in the book, but I just wanted you to hear it from me. So the properties of a normal distribution are that it's a continuous probability distribution for a random variable, and it is the most important one we will use in our course. The graph of a normal distribution is called the normal curve, and it's pictured here below, and that particular curve has certain properties. The total area under the curve is equal to 1. That's to correlate with 100% of your population. The mean, median, and mode are all equal. It's bell-shaped and symmetric about the mean, so that means it follows that 68, 95, 99.7% rule. As the normal curve approaches the x-axis, it never ever touches it. So it technically continues forever. This way and this way. The problem is that eventually it essentially is the x-axis, even though it technically can't touch it. Okay, another neat feature of the normal distribution curve, okay, at least neat from a calculus standpoint, is these points of inflection. The points of inflection are where concavity changes. So if you look from here to here, the curve is concave down, and then from here and here, it's concave up. So like if you, it could, I don't know how to say it. It's like cupped down and then cupped up. That's probably the best way to talk about it. And that change happens automatically at one standard deviation away in either direction. So from a calculus standpoint, that's pretty darn cool. From a stat standpoint, you probably think, eh. Okay, so we have a couple of examples here on the slide, and they've actually already given away the answer, but if you look, the bigger the standard deviation is, the more spread, of course, the curve is, and the faster you're hitting that point of inflection. So these all have the same mean. That's not true. I apologize. The first two have the same mean, but the second one has smaller standard deviation, so you see that the curve is more compact and those points of inflection happen sooner. On this third one, the shape is exactly the same as in graph B because the standard deviation is the same, but the mean is lower, so we just see the whole graph shifted down. The mean gives you your line of symmetry, standard deviation gives your points of inflection. So my slide has already shown our answer, but just ignore it for a second. You can see that A has a smaller standard deviation because of the space here versus the space here in B. Second thing to note is where is that point of inflection happening? So maybe here-ish, and then maybe here-ish, and that's how you can actually calculate what the standard deviations are for each one based on how the curve looks. Okay. Now, the way to interpret this graph is just like you did before, plus or minus 1 standard deviation, 2 standard deviations, 3 standard deviations, and so forth. The nice thing is that we have some calculus that will allow us to find the area more than just in the spots that fall in the pretty places from the empirical rule. So we're going to see z-scores again, taking the value you care about minus the mean and dividing by the standard deviation. But we're going to use those z-scores to recreate a standard deviation that's a normal standard deviation. Instead of using means, this particular graph is going to use z-scores only. So we have a table of values that will calculate this for us. Our table only goes out to negative 3.49 because anything further essentially is 0. And let me skip to the page that I really want to talk about because you guys can go through these slides yourself. We want to look at how to read this normal distribution table. So I'm going to take you into my math lab, and I'm going to show you that if you'll go to Tools for Success and click on Tables, it'll pull up this normal distribution table for you. So I should have that back in my notebook. So let me go find it. Okay, so let's walk through a problem and I'll show you how we use this table. So let me give you big picture, even though maybe we're not really quite ready for it. If I have an IQ score of 108, and I know that the mean is 100 and the standard deviation is 15, the best I could do back in chapter 2, I don't know what's wrong with my brain today, it doesn't want to write what I'm saying. The best thing I could do back in chapter 2 was to say, well, I have a z-score okay, rewind. Let me try that again. The best I could do back in chapter 2 was talk about from 85 to 115 is about 68% of the population. Well, what I'd like to know now is something like what percent of the population has an IQ less than 108. And because 108 doesn't fall in one of these pretty spots from chapter 2, we can't do it with our chapter 2 information. So what this table does for you is if you can find the z-score, then the table will tell you what percentage falls below. So think about this area here that they're talking about. This area is the percent under the z-score you look up. Okay, so area and percentage are the same. So let's take that IQ score of 108 and find the z-score. So the z-score would be the value you care about minus the mean and divide by the standard deviation. That leaves us with 8 over 15, and decimal wise is equal to what? So we get 0.5333. So the way to look up values on this table, if you look, this column has the z-scores to the 10th decimal place, and then you come over to this section to pick up the 100th decimal place. These are all negative z-scores, so I need the second page. And on the second page, I'm going to come to line 0.5 and then come over to the column of 0.03. So this is my z-score. So let's look at picture-wise what that looks like. I'm a big picture person. And so we started with IQ scores that had a mean of 100. One standard deviation was 15. And we were asking the question here at about 108, what is the percentage underneath 108? Okay, well, we can see that that's a little more than half, right? Well, the table is telling me that it's a little more than 70%. So all we did was we changed this information into z-scores instead, and we said here's a z-score of a 0, and the z-score we wanted to look up was 0.53. What's the area underneath the curve? from all the way over here back to 0.53. So we found, I'm going to start calling it a p-value. We found a p-value of 0.7019. That's also the same as about the 70th percentile. Because, right, percentiles is percentage underneath. Okay, well, that's the big picture. But big picture is hard to swallow when you're first learning how to chew. So we need to just take small bites for a little bit. So I'm going to come back with another video that just practices using this table in different scenarios with the table. So thanks. Bye.